Okay, so now we are going to talk about hypothesis testing, which is basically you reuse most of the stuff that we saw during the computation of the confidence interval. So things like standard error, the sampling distribution, they're more or less the same. But now what actually happens is that we're gonna, let's say, build our sampling distribution and our set up this abstract normal distribution in actually around our hypothesis and not around our sample mean anymore. And the reason we will do that is because this fits our idea of what it means to do a hypothesis test. Because what we want to do when we do a hypothesis test, that we want to reject something. We don't want to find out where something is, but actually we want to find out where something probably is not, right? So when we did our confidence interval, we were kind of trying to find this interval where the true population mean was actually probably or likely to be in. So for example, in this case, we say that the population mean is likely to be inside this interval, but we don't know exactly where. Well, it could be here, but it could be also anywhere else with different probabilities. But one thing that we can do when we set up such a sampling distribution is that we can say, okay, anything that's outside of these limits, so either less than the lower limit or more than the upper limit, these are very unlikely to be the true values, right? Or in other words, you can say these values are very unlikely to be observed given that we have set up this probability distribution, right? And this is the idea, that main idea around the hypothesis testing, because when you do hypothesis testing, basically what we do is we define this sampling distribution or this distribution of possible values that we would observe if we repeated this sample many times. And then we say, okay, given that we have this distribution, given that we have this information about what are likely values that we would observe if we repeated this experiment many times, so what is the probability then that I would have actually observed the specific data points that I did observe, like the sample mean that I observed? So if I take the sample mean that I have in my hands, how likely would it be that this would happen if I assumed that the null hypothesis was truth? And that's basically what we're doing here. For example, I'm building the same sampling distribution that I did in the confidence interval, but now it is actually centered around my hypothesis and not my sample mean anymore. And then given that I have centered this distribution around my hypothesis, then it's possible for me to ask questions to, for example, say that these things that are closer to the middle, these are very likely observations. So they're likely to have happened, right? They, if some value is close to the middle, for a definition of close that that we have seen in terms of standard errors, then we say, okay, these things are likely to happen. But if something is very far away from the middle, either to the left or to the right, then they are very unlikely observations. And then the point is, if I have a certain point that I observed, and I find that the probability of observing that point, given the hypothesis, is very far away from the middle, so the probability is very low, then I will reject my hypothesis. Because I will say, okay, I have this sample in my hand, the sample mean, I have computed it. And given, if I assume that the null hypothesis is truth, then this would be very unlikely to happen. So I would say that probably the hypothesis is not true. I will reject the hypothesis. And then I will, let's say, this is the ideal result that you will get when you do such a test. You want to reject the hypothesis because you have an alternative hypothesis that you think that is more likely than the actual null. So the null is the thing that you don't think it's true, so you want to reject it. But sometimes you can't. Sometimes your observed data point is actually quite close to the middle of the distribution. So given the null hypothesis, given assuming that it's truth, then the probability of having observed that point is actually quite high. So in that case, you'll say, well, I cannot reject my null hypothesis because it could be truth. I don't know if it is. It could be true, but it could be also not true because maybe the hypothesis is something else that also makes it my observed point likely. But I cannot reject it because it is within the realm of possibilities, and then we simply don't reject, and then we don't conclude anything out of that. So as in a summary, we will build the same sampling distribution with the same standard error, but instead of building it around the sample mean, we will build it around a certain null hypothesis, right? As we this is all recap, right? We talked about it in the last lecture already, but in this case, the cool thing is that when we need to establish our null hypothesis for this idea of testing for the difference of two values, then that's actually a bit easier than what you did before, because most of the time the null hypothesis is simply that both things are the same. So if I have two different samples and two different sample means, then my null hypothesis is usually, actually almost all cases, the null hypothesis is simply, well, the samples are the same within a certain statistical variance possibilities, right? Or if you say that they're the same, the exact same thing is to say that one minus the other equals zero. That's just this is just another way to write this thing. It's exactly the same. But this is usually the most common way to represent it, because everything that we're doing is actually testing for a certain value that becomes the difference here. And when we go from this one to this one, then you can see that actually we're going back almost to having a hypothesis, a null hypothesis on one sample, because now xa minus xb, if you take them as a whole, they're just one value. And remember, when we were specifying a null hypothesis, we were just saying a certain value equals something, right? So you had a hypothesis that said, well, I think that the average height of the Swedish, man between 14 and 20 is whatever, blah, blah. So it would be some value equals some other value. And in this case, it's exactly the same. It's this thing minus this thing equals zero. And this kind of like is a lot more familiar to us than just saying that they are equal. So, but it's exactly the same. It's just another way to write it. So that makes it a little bit easier because you don't really have to think about it too much. Your null hypothesis is always that they're the same. And then you have to think about, well, what is my alternative hypothesis? So what is the thing that I actually think it's true, that I actually think is like the alternative to the null hypothesis, right? And that's when it comes time to determine if your test is one-tailed or two-tailed. And the difference between two-tailed and one-tailed, if I'm not mistaken, we've also talked about this last time, but just as I guess a quick recap, is that basically a two-tailed test is if you're only interested in testing whether the actual value is different than the null hypothesis. So let's say the null hypothesis is here in the middle, right? And you want to test if your actual difference, your actual observed difference is different than zero. And since we defined here that our null hypothesis is always that the difference equals zero, or that xa equals xb is the same, then you can see here that the normal probability is now centered around zero, because that's the null hypothesis. So if your actual observed difference is somewhere close to zero here, either to the left or to the right, then you cannot reject your hypothesis. But if it's very far away, then you might be able to reject your hypothesis. And when you have a two-tailed test like this, that means basically that you're using the two tails of the normal distribution, this tail and this tail, because you don't know, or you don't care, or it's not important to you if the actual observed value is larger or smaller. What matters is that it's different, right? And then you have to consider both the left tail and the right tail at the same time. That's what, let's say, that's what constitutes this blue area here, is what constitutes the areas where you will reject your hypothesis. Because if your observed value actually falls within either this area or this area, then you reject your null hypothesis, because you say, look, this is very, very far away from the center. So that's the probability of this thing happening is very, very low. and thus I will reject my null hypothesis because my null hypothesis is probably wrong. If it was right, I wouldn't, it wasn't likely that I would have observed this thing because it's just, the probability is just too low. And when you have a one-tail test, you're interested actually in whether the value is actually greater or smaller. So you have an alternative hypothesis that says, look, even though my null hypothesis is actually 0, because that's the standard null hypothesis for difference of sample means, I do have a hunch that the actual value is either lower or smaller or greater than the null hypothesis. So it's like I think that one thing is larger than the other, so I think that the difference is positive, or I think that the difference is negative because one thing is actually, let's say the first one is smaller than the second one. So when I do xa minus xb, I end up with a negative value. And I think that this negative value is really very, very far away from 0. So I will only take the left tail, let's say, because then I say, okay, if it falls within this region here, this blue region here, that is what I consider to be far from the center. This is this blue region, but only to the left, not to the right. And or analogous, you could do the same thing here, but to the right here, and then you say, if my actual observed value falls within this blue region, but to the right, then again, this is what I define as being very far from the center. And so if it does fall within that area, then I would say, yeah, I reject my null hypothesis because it's too far from the center. So it's not likely that this would happen given my assumed null hypothesis. And the reason why this is important is because of how we actually define these blue intervals where the hypothesis is rejected. And you can see that, for example, if you take two tails, then the two tails are actually a little bit smaller than the one tail because these two tails here, they kind of have the same mass or the same area of this one blue tail here. So this one ends up being a little bit larger or a little bit more to the right here, because this entire blue region here has to have the same area as these two blue regions here. And then of course that it changes a little bit. You cannot just ignore one side and take the other, because then you would be taking only half the probability. This plus this equals the actual probability. So for example, this blue area is 0.025, which means 2.5%. So these 2.5% plus these 2.5% here, that makes it 5%. While on the other hand, this entire blue region here is already 5% because you're only taking one side. So this changes a little bit how you compute the actual critical value. And when we did this for the confidence interval, we always consider two-tailed because a confidence interval is always two-tailed. A confidence interval is always a symmetric interval around the mean, or in this case, around the null hypothesis of 0. But when you do one-tailed, a confidence interval can never be one-tailed, but when you do one-tailed, this is not symmetrical anymore. So basically, the difference is that when you're going to compute your critical value, be it however it is, you're going to have to take this into account. So just make sure that at this point you determine whether your test is two-tailed or one-tailed. Then you choose a significance level and find the critical value, and that's where we're actually going to use that. Now, the significance level is your choice. Is your choice, right? 5%, for example, is a safe choice, is a very common choice. 1% is good if you really, really want to avoid rejecting too much of your null hypothesis. So you're going to say, like, okay, I'm only going to reject it if I'm really, really sure that's not true. Because, you know, if you have 5%, then you have this area of 5%. So anything that falls within that area is a rejection, right? You reject the hypothesis. But if you think that maybe that's too much, maybe it is still possible, maybe it falls within that area, but you think, well, maybe it's still possible that actually the hypothesis is still true, even though it did fall into that area, then you can shrink it even more to 1%. And then you say, okay, I will only reject this if I'm really, really sure that it's not possible. But on the other hand, of course, you end up maybe something falls outside of that blue area and you don't reject it, but it might have been rejected. So it's really a trade-off, and 5% is usually a safe choice, but 1% is also good. And if you actually manage to reject in the 1% significance level, then it's like, that's a very, very, very confident rejection. So it's actually really good if you can do that, and that's what would be a great result. But again, depends on the problem at hand, depends on how you want to do it. Usually we'd go with 5%, and I would say that probably you guys could go with 5%. Then comes the time of determining the critical value, because as soon as you define your significance level of 5%, for example, now comes the time to say, okay, how far away do I have to be from the center? So that blue area that we saw before, how far away do I have to be in order to actually have these blue regions that corresponds to, for example, 5% in that case? Because the values that we see here, or here if it's one-tailed, these areas, they represent a percentage of the entire curve, or of the entire distribution. So as soon as you determine your significance level, like 5%, then you have to determine what is this critical value here. For example, in this case, 1.96 or 1.645. What is this value, this critical value over here, that actually breaks my distribution into these areas where I get this 5% or this 1% that I have defined as my significance level, right? And that changes. Even though before, when we did it, actually, if you wanted 95%, then you could use either 2 or 1.96. Then that was kind of like fixed. That was fixed because we were using Z distributions, purely normal distributions, which were not really realistic. But in this case, we are going to use a T distribution, which is it's still normal, but actually the estimates change depending on your sample size. So in order to be more realistic, more accurate, when your sample size changes, the actual distribution will also change, and by consequence, the critical value will also change. So based on your significance level and based on your degrees of freedom, you will have then a certain specific critical value, and that's the value that you need to use to like break your distribution into two parts, inside and outside, or gray and blue, based on the previous picture that we saw. So it's the same thing that we did with the confidence interval, but this time it may be one-tailed. So then you either use a t-table or online calculator or anything like that, and then you will find your critical value. And remember that you will need, again, the degrees of freedom, and again, the degrees of freedom are the minimum. So the smaller sample, if they're different, -1. So if they're equal, then it doesn't matter, right? They're both the same. But if they're not equal, then you take the smaller one, the size of the smaller sample, -1. And then if you want to see this, I'm not sure if you can see this actually. Let's see. Yeah, if you want to see an example of this, this is a calculator for critical value. You can find lots of this online, for example, if you want to use them. Now, one interesting thing about this one is that this one is one-tailed, right? So it doesn't give me the option of doing it two tails. And I guess this is the same that we saw in the previous video. So again, if I wanted to compute here sorry. Again, as we saw before, if I wanted to compute the critical value for 5%, for example, but I'm actually having two-tailed hypothesis, or my test is two-tailed because I want to consider both sides, then I would actually choose the half of 5 here for 2.5%, because again, this would give me the critical value for one side where it has 2.5%, and also for the other side, which is the same for also 2.5%, right? So if I take some critical value here, like for example, let's say my sample has 30, my two samples are the same and they have 30, for example. So my degrees of freedom are 29. Did I calculate for T, and then it gives me 2.05. So basically what this means is that I go 2.05 to the left and 2.05 to the right. So let's say minus 2.05 because we're centered at 0, plus 2.045. And that's why I chose 2.5%, because then I have 2.5% one side, 2.5% in the other side. On the other hand, if I was actually doing a one-tailed test and I was still using 5%, then I would simply compute this critical value one tail, and then it would be 1.699. And then you can see how 1.699 is closer to the center than 2.05, because now I take this 1.695 and then everything that's outside of that is actually 5%, and everything that's inside of that up to everything, so it's not symmetric anymore, it goes all the way into the end, that is 95%, right? So we have to make this distinction between one tail and two tails. You have to be very careful when you're actually computing the critical value, so that you make sure. Some calculators, some online of these calculators will actually give you the option to do it two-tailed. So then it doesn't matter. You don't have to worry anymore. So if it says it's two-tailed and you take 5%, then it will give you the right value anyway. I wanted to show this possibility of having to like do it in your head, just to make sure that you guys pay attention to this when you're doing it and you don't make a mistake on that. Yeah, and then now we're basically ready to kind of like do the test. And the fourth step is to determine the test statistic of your observed difference of sample means. And this we didn't do in the confidence interval. So basically we're going to compute this t thing, which is our test statistic. What does it mean? Well, this is kind of like a way to represent our actual observed value in a way that it makes it easy to do the statistical test, right? And basically it's very easy. We're just going to take the observed difference that we had, so xa minus xb, and then we're going to divide it by our standard error. And the standard error here is the same that we computed before in the confidence interval, so we know already how to compute this. And then basically we just divide our observed difference by the standard error. And what this does is kind of like it scales down or either down or up, depending on what was the original scale. But basically it kind of positions it within the distribution. And as soon as it positions our value within the distribution, so it's almost like, if we go back here, when we compute the test statistic, the t, it's almost like we're putting it in this scale, in this ruler here, and so to speak. And then it either falls, like, for example, the t will be like, let's say 1.5, right? Let's say the t of our observed sample mean is 1.5. Then it falls within here, like somewhere. Well, if it does that, then you know that it is not a rejection, because it's inside the gray area where it's not extreme enough, as we say, in order to reject your null hypothesis. So it's actually likely that it would happen given the null hypothesis, so you cannot reject null hypothesis. But on the other hand, if it was like 2.4, then it would end up being somewhere over here in this line here. And then you would say, nope, this is not very likely to happen given my null hypothesis, so I will reject my null hypothesis. And to the other side, it's exactly the same. It's just that it's negative number. So it's like, if it's minus 1.5, then it falls somewhere over here, not reject. If it's minus 2.3 or something, then it ends up being somewhere over here, then that's not a rejection. And again, same thing here. And let's say minus 1.5, not a rejection, because it would fall somewhere over here. Minus 2.3, rejection, goes somewhere over here. And the only difference is that if you compute your t, and let's say your t is like 2.3, that will be very far away to this side here, that is still not a rejection. And that's the difference between the one tail, the two tails, because if it's very far away from the mean, but it's to the right here, in this case, because we're looking to the left, then it's not a rejection, because my alternative hypothesis, I have stated that I was doing a one tail test to the left. So anything that happens to the right is not a rejection for me. So then just keep that in mind, guys, that when you have a one tail test, it actually matters which side of the zero you are. So extreme values to the right here would not mean a rejection. Only extreme values to the left here, like minus 2.3, that would be a rejection. This blue area is like your critical area. And that's how you take this t. And as soon as you take this t, that's it. The test is almost done, because you can just very directly take this t and compare this with your t star, which was your critical value that you computed based on your significance, right? So your first critical value was like 1.96 and your t is 1.5, then that's it. you can very easily just compare t with t star and say, okay, t's is, let's say my t star is positive, so it is to the right, and my t is less than that, so no, it's not rejection, period. That's it. That's your hypothesis test. As soon as you have your t and you have your t star and you compare them, then you immediately know whether you're rejecting your hypothesis or not. And formally you say that you only reject your hypothesis if your t is more extreme than t star. And when I say more extreme, why do I say more extreme and not like smaller or larger? It's because it depends on which side you're looking at. If you're looking to the negative side, then more extreme is actually less, it's more negative, right? So it's less and less and less. But if you're looking to the right for positive t star, then actually more extreme is larger, so it's larger and larger and larger. And then so that's why I say more extreme, because it's basically means something that's far away from the center, whether smaller or larger. And this is it. This is a hypothesis test, period. T compared with T star. However, there is this other more common way of, let's say, doing this. Not more common, but more detailed way of doing this, which is actually to move on and compute the p-value. So the p-value, p comes from probability, right? I mean, we've talked about this before. It's kind of a recap, but p comes from probability. And the p-value basically is what is the probability that these specific t that I just computed, so I computed the t, and now I'm going to say, what is the probability that such a t will happen given the null hypothesis? And basically, again, you're going to, as soon as you have the t, all you have to do is actually go back and do the exact same thing that you did with your t star in order to compute the critical value, because the t is again a t statistic, as the t star was also a t statistic. So you do exactly the same thing. You take some kind of an online calculator, then you will compute, you will choose how many degrees of freedom you have, if it's one-tailed or two-tailed, then you give your t, and the calculator will tell you the probability of that, or the p-value of that is something like 10% or 1%. And again, that when as soon as you have your p-value, which is the probability that whatever you computed or whatever you observed actually would happen, then you will compare that with your significance value. And then all you do is say, okay, is my p-value smaller than my significance level? Yes, then I reject my hypothesis, because the interpretation is, since my significance level of like 5%, that's where I draw the line, right? That's where I say, look, anything that has a probability of less than 5% of happening, I'm going to reject that. And so if your p-value is less than 5%, then you reject it, because you say, I consider this to be too unlikely to be possible to happen given my that I assume that my null hypothesis is true. So, and both things are exactly the same, because if the t is more extreme than your t star, basically that translates directly to your p-value being less than your significance level. Both things are like completely attached to each other. They're exactly the same. And I guess the right thing to do is just to report on both. But basically they're the same. If one thing's a rejection, the other is also rejection, and so on and so forth. They basically come from the exact same computation, right? It's just that the p-value is a little bit more detailed, because then you actually know the probability, right? So you know exactly, like it's more interpretable, let's say. It's easier to understand what it means than just a t statistic or something that means nothing. It's just a comparative thing. And basically, yeah, so in order to compute a p-value, let's again just look at it as an example from the same calculator. It's a similar calculator from the same website. And in this case, the first thing that they ask me is my t-score. And again, my t-score, as you know, is this thing here, right? So we know how to compute this. It's very simple. It's just take my observed value, divide by my standard error. That gives me my t-score. And then I will go there and then I will take, let's say I will put here a t-score of whatever, 2.35. I'm just making it up. And then again, degrees of freedom. Why? Because as we talked about, this is a t-test, not a z-test anymore. So for a t-test, depending on the degrees of freedom or depending on the sample size, the results change. So again, I will take my smaller sample, and let's say again that my smaller sample it has 30. So I'll put 29. Significance level. Now pay attention here. If in this case, I can choose whether I want one tail or two tails. So this thing actually has to be your actual significance level. So don't, if you can choose between one tail and two tailed, so you don't have to play around with the values anymore. You just do what, use what you have. So I will leave my significance level at 5%, and I will say that my test is one tailed, and I will compute, calculate. And basically, yeah, my p-value is 0.0112, blah, blah. So this is basically 1.29%. And 1.29% is less than 5%. So basically, I rejected my null hypothesis because the probability or the p-value or the probability that my observed value would happen given my null hypothesis is actually too low for me to accept or to think that the null hypothesis is likely, so it isn't, and I reject it. And as soon as you did that, that's it. Basically, you have your hypothesis test. You did it. That's it. So t statistic, p value, then compare with the baseline that you set for yourself. Period. That's done. All right. And basically you see how this kind of ties up very nicely with the confidence interval. There's actually a very nice symmetry between the hypothesis test and the confidence interval. And you could even reject your hypothesis just by looking at your confidence interval. It's just that the way that we're doing right now, it's more like a formal, more common standard way of doing it. So this is how you would do it.